We can now look at total derivatives, and if we consider a function like this, y is a function of x as well as w, with a total derivative now, we can allow for a relationship between x and w. So this is for a total derivative, and if you recall, for a partial derivative, we could not have a relationship between x and w. All right, so to calculate a total derivative, we need to start with the total differential, dy in this case. So if you set out the total differential dy, okay, it would be as follows. All right. And if we know that x is a function of w, then that means that w is acting indirectly upon y through the function g and directly upon y through the function f. So in other words, w is the ultimate cause of a change in y. So we need to vary w and x at the same time to find the total change in y. We can set all of this out in a channel map, which is this figure here. And as stated above, in this model, the ultimate source of a change in y is w. W affects y directly through the function f, and indirectly because it affects x through the function g, and then of course x affects w through the function f. So this top channel here is depicting the indirect effect. What we also need to remember is that a partial derivative would be able to explain the direct effect of w on y. But when we have both these direct and indirect effects, we need a total derivative in order to work out the total change in y. So if we work with the function y equals a function of x and w, and then we further know that x is a function of w, then as we saw in the previous slide, that ultimately w is driving the change in y. So we want to find the total derivative dy dw, and this measures the rate of change of y with respect to w, and it is basically a ratio between two differentials. So we have two simple steps to follow in order to calculate this total derivative. Step 1, we need the total differential dy. Okay, so as we saw in the previous slide, here we have our total differential dy. The next step, step 2, we simply divide both sides by dw. dw in this case is the relevant differential because, as we've said in this model, w is the driving force of change. So quite simply, if we take this differential and then divide through by dw, we end up with this here. All right, so each term we've divided by dw, all right? And on the next line, we can see that we can simplify, because if we look at this term here, dw divided by dw will give us 1. All right, so this here would be our total derivative. And as we can see at this box in the bottom, the total effect, so the total change in y, will come from an indirect effect of the change in w and how that affects x, and then how x affects y. So that's the indirect effect of w on y. And then, of course, we have the direct effect, which is the direct effect of w on y. Let's work with this example here now, where we have y is a function of x and w. And we can see here we've got 3x squared minus w squared. And further, we know that x is a function of w. So we can see that ultimately the change in y is being driven by w, both directly here as well as indirectly through x, given that x is a function of w. So you want to work out the total derivative dy dw. You want to know the rate of change of y with respect to w. And we are working out this total derivative, remember, because we are allowing x and w to vary at the same time. And furthermore, we know that these variables are related. We know that x is a function of w. So because of all of that, we need to find the total derivative in working out the change in y. So our starting point is to set out the total differential dy, which we see here. Okay, and we then need to divide by the relevant differential, which in this case is dw, because as I said, the w is the driving force in terms of changing y, indirectly and directly. So we divide both sides by dw, right? And recall, when we divide dw by dw, this will equal 1. All right, so we have a 1 here. Okay, so this here is the total derivative, dy dw, and we can now work this out. So the one thing we just need to be careful of, or we need to remember, is when we see this dy dw with this notation here, we are looking at the total derivative. Okay. On the other hand, if we use this curly d here, right, this notation here is the partial derivative. Okay, so we just need to be mindful of that in working out our total derivative dy dw. So we start off, we need to work out this partial here, right? We need to partially differentiate, we need to differentiate y with respect to x, all right? And we are finding the partial derivative, so we would be treating w as a constant in that case, all right? So if we find the derivative, or if we partially differentiate with respect to x, we're going to end up with 6x using the power function rule. And that's what we see down here. Okay, so 6x is this here. All right. Our next step, we need to find the derivative of x with respect to w. All right. So to work this out here, we need to work with this function here. X is a function of w. All right. So we need to differentiate with respect to w. Using the power function rule, we'll end up with 4w plus 1, right? 4 is a constant, obviously, so that would be 0. So 4w plus 1. We go down here, we see 4w plus 1. So that is this here. Okay. And then lastly, we need to find this partial here. So we need to go back to our y function and find the partial derivative, okay, with respect to w here. So in that case, we're going to treat x as a constant, right? And if we partially differentiate, we're going to end up with minus 2w, all right? So if we go down here, we have minus 2w, which is this here. Okay, so just to recap, this here, 6x, here, 4w plus 1, this here, minus 2w. Okay, and there we have it, the total derivative, dy dw. And we refer to this process of finding this derivative as the total differentiation of y with respect to w. Okay, and you can check this by substituting the function g. Okay, this would be the function g in this case, into f, and working out the derivative that way, and you would see that you would get to the same answer.